Okay, so in this video we're going to be doing trigonomic ratios of acute triangles. So if you remember, acute are angles that are less than 90 degrees. So when we are dealing with angles that are less than 90 degrees, that means we have one angle that is 90 degree in the triangle. Well, not necessarily, but what we're going to be doing in terms of trig ratios, just to recap. SOHCAHTOA, sine, opposite, hypotenuse, cos, tan, and A is adjacent, and hypotenuse, and O is opposite. So we have our SOH, sine theta is equal to opposite over hypotenuse, cos theta is adjacent over hypotenuse, tan theta is opposite over adjacent. So now that we have our trig ratios, we can look at an example like that one. Say we have an angle of 16.7 degrees. And I want to find out, let's say I have a 3 meter height here. I want to find out this guy right here. Let's call this x. So let's say I want to find that out. So I'm going to be using my tan ratio because I have an angle and then I have the opposite and I'm looking for the adjacent. So I can do tan theta equals O over A, which tan theta is equal. This will now be written as tan of 16.7 degrees is equal to opposite, which is 3 over x. So now if we were to rearrange this, we can put this as x equals over tan 16.7 degrees. And if we were to punch this into the calculator, say we do that, I have tan of 16.7 is 0.3, and if I do 3 over that, I get 9.9999, which is about 10. So our x is equal to 10. So if you have something that is 10 meters long and 3 meters high, or 10 meters away and 3 meters high, the tip of that to here is going to be 16.7 degrees. And yeah, like, this video is kind of more of a recap of things that we have done in the past. So let's say we have another problem where we have this triangle 28, and this is a right angle. So say I want to find out this length here, and again, as a recap of what we used to do in the past, this is basically one of those A 20 squared is 400, 8 squared is 64, so 464, and c is equal to the square root of that. So I would end up with about 21.5. And now we have three different angles here. Sorry, that one's 90. But we have these two, theta 1 and theta 2. And I could actually start solving for these. Say I wanted to solve for this one, theta 2. I know that the tan of theta 2 is opposite which is 8 over 20. So I can put that in. 8 over 20 is about 0.4. So tan of theta 2 is 0.4. And if I was to punch that into the calculator, I could do inverse tan of 0.4. I get about 21.8. I can round that too. That's how I write, or you write, everybody writes inverse tan. And now I have 21.8. Now, I could actually use another trig ratio to find this one. I could do the tan of this one and make that the opposite, and that's the adjacent. Or I could do a cos, where this is the adjacent and that's the hypotenuse, or opposite and hypotenuse. I could use each one of them. Or I can do the rule where the angles inside a triangle all add up to 180 degrees. So 90 plus 21.8 plus I have theta 2 and I'm looking for theta 1 is equal to 180, so theta 1 is equal to 180 minus 90 minus 21.8. So that is going to give me 68.2 degrees. And I don't know if we have gone over reciprocal functions, but let's introduce them here. I doubt we have. But basically, when we have something like sine theta, there is a reciprocal function of this, which is cosine. The word is literally slipping my mind right now. CSC. I believe it's cosec. No, yeah. I'll have to come back to that. And for our cos theta, our inverse is sec theta, and for our tan theta, our inverse is cot theta. And CSC is the same as, or is equal to 1 over sine theta. That's what the reciprocal is. As our sec theta is 1 over cos, and our cot theta, cotan, is 1 over tan theta. So while you might remember sine theta is opposite over hypotenuse, CSC theta is the reciprocal. So our hypotenuse over our opposite. While cos theta was our adjacent over our hypotenuse, the reciprocal is now our hypotenuse over our adjacent. And while our tan theta was opposite over adjacent, our cotan theta is now adjacent over our opposite. So these are our 6 trig identity or functions, our ratios, our sine theta, our sine, our sine, cosine, and tan theta. And then we had our reciprocal functions here. 1 over sine CSC theta, sec theta, and cotan theta. So, I hope you remember these because we're going to be using them in the future in much more confusing ways. So for now, that's all for this introductory video to these trig ratios, and I shall see you in the next one. Okay, so in this video, we're going to be looking at special angles. So special angles, as we'll learn, are going to be triangles with 45-degree angles or 30 and 60-degree angles. So, say we have this, where this is 45, this is 45, and this is 90, right? If you were to just flip that, you'd get a square. And then we have the other one where we have 30 and 60 degrees, and that's alright. And if you were to flip this, you would get a triangle. So we can actually calculate the sine, cosine, and tangent for this one, our 45-degree angle. So if we were to have these angles being the same, that would mean that this length and that length are going to be the same, because if they varied, then we would have different angles. So say we have this side is equal to 1, and this side is equal to 1, right? If I want to find out the hypotenuse, I could use the Pythagoras theorem to find that out, which is 1 squared plus 1 squared equals, let's call it h squared. 1 plus 1 is 2. So the hypotenuse is the square root of 2. There you go. And now let's look at, because I know these are 45-degree angles, and it doesn't matter which angle I look at, cosine or tangent, from whichever angle, I'm going to get the same ratios because they're the same from whichever angle you look at. So let's look at an angle through our trig ratios, which is, let's do sine first. Sine 45 is equal to opposite 1 over hypotenuse, and then hypotenuse, which is the same, 1 over, and then our tan 45 is equal to opposite over adjacent, 1 over 1, which is 1. So, there we go. One thing to note, this root 1 over root 2 is the same as root 2 over 2. It's just easier number to use when doing calculations. If you continue to pursue math or a field in math, you're going to actually memorize all the sine, cosine, and tan values by heart for 45, 30, and 60 degrees, and 0 and 1. But I can actually show you an easier way to remember that. So let's look at this. Our 60 and 30. So say we have 60 and 30. Let's put this as 1. Let's put this as 2. And let's call it 30, and that's 60. Now, one second. So if we have 2 as our hypotenuse and 1 as our one of our edge values, then through Pythagoras theorem, we can do 2 squared is equal to 1 squared plus, let's call this x squared. So 2 squared is 4 minus, I'm going to bring this over 1. So the square root of 3 is x. So I'm just going to write that there, root 3. So now let's start writing the trig ratios for 60 degrees. So for sine, let's do 60. Sine 60 is opposite root 3 over the hypotenuse 2. Cos 60 is equal to adjacent 1 over hypotenuse 2. Tan 60 is equal to opposite over adjacent, which is root 3 over 1, which is just root 3. Similarly, I can write them out for sine. So, if I was to do them for sine, then sine opposite over hypotenuse 1 over 2. I have cos of 30, which is adjacent over hypotenuse root 3 over 2. And then I have 1 over, tan opposite over adjacent 1 over root 3. And again, root 3 over 3 can also be written as 1 over root 3 can also be written as root 3 over 3, just to make it easier in calculations. When can you actually use these identities, these special values? Say we have a problem where we want to do sine 45 times cos 45 plus sine 30 times sine 60. So I know that from my special angles. Let me just put them in for reference. Sine 45 is root 2 over 2, which is 60 is root 3 over 2. So now that I have my values for my special angles, I can just do my fraction math. Root 2 times root 2 should give me 2. The denominators will multiply. Root 3 over 4. And now I'm left with let me write it here. 2 plus root 3 over 4. And you can actually punch all this into a calculator and punch this into a calculator. They'll become the exact same value. So, one thing I can actually show you that one of my favorite teachers showed me in school is the sine, cos, and tan values of 0 degrees, 30, 45, 60, and 90. I can make a chart from this very quickly. And that is by doing this. I can do 0, 1, 2, 3, 4. I just write down 0, 1, 2, 3, 4. Put them, square root them all. And then put them over 2. And now let's just evaluate these quickly. 0 over root 2 is 0. Root 1 over 2 is 1 over 2, because the root of 1 is 1, so 1 over 2. Root 2 over root 2, it's not get simpler. Same with this one. Root 4 is 2, 2 over 2 is 1. That's my first row. The second row, I'm going to write this backwards. So I'm going to write 1. I'm going to write this 3 over 2. I'm going to write, well, this one doesn't change in order. And I'm going to put 1 over 2. I'm going to put that 0 here. Now I'm going to take this value and divide it by that value. 0 over 1 is 0. 1 over 2 divided by root 3 over 2. 1 over 2 divided by root 3 over 2, which is flipping and multiplying, so 2 over root 3. These cancel, so I'm left with 1 over root 3. And then I have root 2 over 2 divided by root 2 over 2. These two values are the same, so that's just going to be 1. And then this one, let me write it somewhere here. Root 3 over 2 divided by half, so multiplied by 2. These cancel, I'm left with root 3. 1 over 0 is undefined because you can't divide by 0. So now I have this chart of 15 values. I'm going to write sine here, cosine here, tan here, and then I can write 0, 30, 45, 60, and 90. There you go. I used to do this in the beginning of trick tests just so I have all the special identities. These are my degrees. Sine of 30 is half, cos of 60 is half, tan of 45 is 1. It was a very quick way to just, instead of just memorizing everything, I was able to just chart this out really quickly by doing these 0, 1, 2, 3, 4, square root all of them, divide them all by 2. Writing them out, reversing the order, dividing it to get the 10, and boom. That is how I cheated my way through math. But yeah, those are special angles. I didn't show 0 or 90 in this one, but in future videos when we're dealing with circles, you may actually see them, so stay tuned for that. But for now, that's all for this video, and I shall see you in the next one. Okay, so in this video, we're going to be looking at trig ratios for angles between 0 to 360 degrees. So up until now, we've been really looking at acute angles, so less than 90 degrees. Now we're going to be looking at angles bigger than 90 degrees. So the main difference is that all the triangle angles we've been looking for, if this is 90 degrees, this is 180 degrees, this is 270 degrees, technically this is 0 and also kind of like 360. But yeah, that would be a full circle. Basically, when we have an angle, or in our videos, our past couple videos, when we've been doing trig ratios, we've been looking angles really over here in quadrant 1, and this is quadrant 2, quadrant 3, quadrant 4. Here we have 0 to 90 degrees. Here we have 90 to 180. Here we have 180 to 270. Here we have 270 to 360. So this is going to be very important for us. Up until now, we've been doing our sine, cos, and tan ratios in quadrant 1 with 0 to 90 degrees. But now we're going to be looking at problems that are going to go into quadrant 2, 3, and 4. And one thing to remember is this. The cast, C-A-S-T. Remember quadrant 1, 2, 3, 4. Cast, C-A-S-T. Yeah. If I remember that correctly. No, wait, I messed this up. It should be C-A-S-T. That is correct. Ignore this. So, remember this cast. All this basically means is, in quadrant 1, when we have A, that means sine, cos, and tan. When we do any of these operations on the angle, we're going to have a positive output. So it's going to be a positive number when we do the inverse sine or inverse cos or inverse tan. In quadrant 2 we have an S, so here only sine will be positive. The other two will be negative in this quadrant. Similarly, in quadrant 3, only tan will be positive. Sine and cos will be negative in quadrant 3. And in quadrant 4, we have cos, that'll be positive. And sine and tan will be negative in this quadrant. So these are just some things to remember as we start looking into these things. Let's start with maybe an example. We can do quadrant 1. Let's say we have a point on a graph 3, 4. That is my line. So I know from this triangle and this theta, this is basically the triangle I'm going to make 3, 4, and I know from Pythagoras theorem 3 squared plus 4 squared is 25. Square root of that is 5. this angle to the nearest degree. Let's just, we can do any sine, cos, or tan. If I write out the trig ratios, sine theta is opposite over hypotenuse, which is 4 over 5. Cos theta is equal to adjacent over hypotenuse. Tan is opposite over adjacent, which is 4 over 3. You can punch any one of these into the calculator, and your theta will give you 53 degrees. And notice how these are all positive ratios, because we are in quadrant 1. But let's say, instead of in this quadrant, I want to choose it in this quadrant over here. I choose to do -3. And the same y value. Now I want to find out this angle. Now, let's try doing the exact same thing. Well, for one, our Pythagoras theorem will give us this to be the same because we're squaring it. Doesn't matter if it's -3 squared plus 4 squared. This is still going to be positive, so that's 9 plus 16. Right. So, if we were to write these trig ratios out again, now we have this 4, 5, but -3 here. It's in the negative, on the negative x-axis. And I'm looking for this angle, so if I was to write these again, sine is equal to opposite 4 over 5. Cos theta is equal to adjacent -3 over hypotenuse 5. Tan theta is equal to opposite over adjacent over -3. So that's a negative. Now you see why, from our CAS system, S in quadrant 2 is the only one that is positive. The other two are negative ratios because they're in this quadrant. And you'll see that once we go into tan, if we do the same, well, again, if you were to do these inverse of these, you should get the same. Theta equals 53 degrees. Let's do another one. Now let's go into the next quadrant. If we were to go into quadrant 3, like down here, -4, -3. Let's go like this, -4, -3. This is still going to be a positive hypotenuse. So, now, if you were to write for these angles, if you were to write these out, you would get sine opposite over hypotenuse, -4 over 5. Cos theta is equal to adjacent over hypotenuse. Surprisingly, tan opposite over adjacent, -4 over -3. The negatives will cancel out and you're left with 4 over 3. And that's why your tan is positive in quadrant 3. And now let's do the last one. -3, no, this is positive 3 and -4. That's the point. Angle, and we still have 5. If you were to write these out, sine theta is equal to opposite -4 over +3. Sorry, that's basically what it is. So, another thing that I didn't do though is explain to you the angles when it's in different quadrants. So, if you were to solve for all these thetas, you would get 53 degrees. But 53 degrees only makes sense in this one. Like this right here. But over here, we have to take the angle starting from this line here. So from here to here is what? If this angle is the same as that angle, then we have to do 180, which is this line here, a full 180 minus theta, which is the one that we found. 180 minus 50. 3 is 127 degrees in there. And then similarly, we have to do the same for quadrant 3, which is here. And that is from here all the way. Like that. So now we have 180 plus 53. And that will give us 233. And then we have our final quadrant, which is going to be here. And this is much easier. We just do from here all the way around. A full circle would be 360. And we're going to do 53 less than 360. And we're left with 307 degrees. So there you have it. We have 53 degrees, 127, 233, 307. That is how the cast system works. And this is going to come in handy for us when we start using logic to come up with where the angle is. So if I was to tell you that, for example, CSC theta is equal to negative 2 root 3 over 3, and I was asking you where is this? So by logic, you can just do, this is 1 over sine, so just take the reciprocal of that. So sine theta is equal to negative 3 over 2 root 3. And if you have a negative sign, that means it cannot be in quadrant 1 because everything is positive in quadrant 1. It cannot be in quadrant 2 because sign is positive there. It has to be either in 2 or 3. And that's where, and in quadrant 2 and 3, that's where theta is, the angle. When we solve for theta equals, if you put the inverse of this into a calculator, you should get, let me try punching this in. 2 times root 3, 3 over answer, times negative 1, inverse sine. Oh, I get negative 60. So yeah, I get a negative 60. So that means my negative sign in my negative sign ratio, which we have said is going to be in quadrant 2 or 3, I have 180 plus 60, or 360 minus 60. So now I have either 240 or 300. These are my two solutions. And that's how we're going to be solving trig ratios moving forward using the cast system here, because this is going to be very important to understand. and understand why certain things are positive or negative in each quadrant because of how the ratios apply. So that's all for this video. It's just an intro to the gas system. And I shall see you in the next one. Okay, so in this video we're going to start looking at trig identities. And trig identities are going to help us when we start doing solving trigonometric equations and simplifying them. So right off the bat, let's do the ones we already know. We had our sine, cosine, and tan. We had these three already. So we remember our reciprocal functions. Those are going to be our first ones. Our CSC is 1 over sine theta. Our sec theta is 1 over cos theta. Our cot theta is 1 over tan theta. These are the ones we already knew from our previous videos thus far. So one of the identities that we're going to look at is this one. And this is always, well, this is just a true fact in terms of what it is. So why we can actually prove this if we have a triangle, right? Theta, and let's call it x, y, and z. And if we were to write this out, we have sine theta is equal to y over x. Y opposite over hypotenuse. Y over z. Cos theta is x over z. And we have tan theta is equal to opposite over adjacent. So y over x. So if we were to divide these two, sine theta over cos theta, which is, if I was to plug these numbers in, or variables in, ratios divided by this will become a flip, we'll cross multiply, but basically y over z times z over x. The z will cancel and you're left with y over x, which is, therefore, well, I'll just write, therefore, this identity is true. So now we can do another one. If we were to do the exact same logic as this, there's another identity. So we know that sine squared theta, which is just like saying sine theta times sine theta. We don't write sine theta squared, we write sine squared theta. So we can put that in y over z squared plus x over z squared. And if you were to actually open up these brackets, like do the order of operation, you have y squared over z squared plus x squared over z squared. So now you have x squared plus y squared over z squared, right? And sides that we use to find out the hypotenuse using Pythagoras theorem. So in this case of the Pythagoras theorem, I'll write it here. X squared plus y squared equals z squared. So using this logic, x squared plus y squared is equal to z squared. I can rewrite this numerator as z squared, and I still have z squared in the denominators. That's 1. That's why this is equal to 1, and this identity holds true. Let's look at another one. We have another one. Let's do 1 plus So let's start looking at this. How can we prove that this identity holds true? Basically, I'm going to do it in 2 steps. 1, I'm going to do this side. C as c squared theta is the same as 1 over sine squared theta, which is the same as 1 over sine theta squared. Remember this is my, let's call it my right side. Now my left side. 1 plus cot theta. Remember, cotan is 1 over tan. So similarly here, 1 plus I don't want to skip steps here, but basically remember, tan theta is equal to sine theta over cos theta. So 1 over tan is going to give me the reciprocal cos theta over sine theta squared. That's still here. So cot theta is equal to that because sine theta is equal to sine over cos. So cot theta will be equal to the reciprocal cos over sine. And remember, we still have the squared sign here. So that's all I did. And now the next step, I'm going to put the square in. 1 plus cos squared theta over sine squared theta. That's all I did. I brought that in. But now, if we were to add this, like this 1 plus that, if I was to make a common denominator, I can do sine squared theta over sine squared theta plus cos squared theta over sine squared theta. So, what do we have here? All I did was take this 1 and turn it into a sine squared theta over sine squared theta, which is still equal to 1. And now now that I have the common denominator, I can just add these two. I have sine squared theta plus cos squared theta all over sine squared theta. And if we remember our identity, sine squared theta plus cos squared theta equals 1 from our Pythagoras theorem, that means the numerator is now 1 over test or something, you get this. Say, they give you this and say, prove it, that tan theta is actually equal to all this. So, tan theta, I'll leave it as is. The only thing I can speculate about that is tan theta is equal to sine theta over cos theta. That's all I have. I'll leave that on that side. On the other side, what can I do? First, I have sine theta in both terms in the numerator, so I can factor that out. So I have 1 plus sine theta. Now my denominator is still the same. And look at that. I have in the numerator and denominator 1 plus sine theta. I can cancel that out. And boom, I'm left with sine theta over cos theta, which is also equal to tan theta. And that's how simple it is. You don't have to let any of this intimidate you. Just remember your identities. Remember who you are. Wise words of Mufasa. Okay, so that's all for trig identities. Actually, that's not all, but for now, that's enough for the basics. In future videos, we'll cover more and apply more. But in terms of this video, that's it. And I shall see you in the next one. Okay, so in this video, we're going to be looking at the sine law, more of a refresher. Sine A over A is equal to sine B over B, or even inversely. Where the lowercase a and b represent the length of a side, and the uppercase represents the angle. So say we have a problem like such, where we have C, A, and B, where B is 7.8 meters, A is 5.9 meters, and this angle is 36 degrees. And now I want to find out the angle of B. So, let's start plugging in some numbers. Remember, this is a refresher, so you should know how to do this by now. If not, you can go back into previous or old videos, and I have it explained in those ones. So let's do A. Let's do 5.9, and over its opposite angle, sine 36 degrees is equal to 7.8 over sine B. So, with a little bit of rearranging, I'm going to bring the sine B up to that side. Multiply this sine 36 up that way, and bring that 5.9 down here. And I'm left with this. Yeah. So my B is equal to the inverse sine of 7.8 times sine 36 over 5.9. And if I punch that into a calculator, I should get 51 degrees. And now, with my triangle law, I know that 36 plus 36 and 51 from 180 to get 93 degrees per C. And there you have it. And now, with that angle, I could just simply punch in the same 5.9 sine 36 is equal to sine 93 that I got. That's that one over C. So now C is going to be 5.9 sine 93 over sine 36. Punch that into a calculator and I got about 10 meters. Remember, I have meters in my units always. So, yeah, math is really definitely fun. So, let's look at another example of another triangle. Let's do one with bigger angle. Let's say this angle is 140 and I have this 15.6 meters here and 36 meters here. So, let's say that this is an imaginary axis and I want to find out the angle here. How am I going to do so? And let's say this line here is going to be parallel to the ground. I forget how to spell. Anyways, so let's try to find this angle. And from our angle laws, we know that when you have a C shape, this angle is the same as that angle. So actually, I want to find this angle. And now it just comes back down to a silly sine law equation. So if we start punching these numbers again, we have this sine theta is equal to sine theta over its opposite length, 15.6, is equal to sine 140 over my 36. So if I multiply both sides by the 15.6, this will cancel out and I'm left with sine theta equals 15.6 times sine 140 over 36. And yeah, if I start punching this into the calculator and take its inverse theta, then I should get about 16 degrees, or 16.1 or 2. But basically, once I found this angle, I can say that that is equal to this angle. And there you go. That is a quick refresher of the sine law. I think next we're going to be looking at the cosine law. Just as a refresher for, actually, you know what? Why split it into two videos? Let's just cosine law. Yeah, it should have been. If I'm looking for, let me do this in a different light of color. Let's do this one. I have a squared equals b squared plus, I need more space. And as well as, yeah, that should basically be it. Because if I have any triangle, so if I have these two that I'm looking for, well, basically cosine law, if I have the three sides and I'm looking for one angle or any angle, I'm looking for an angle, I can use this. If I have A, B, and C, similarly, if I have, say, A and, well, let's say I have C and B, and I have the angle in between. If I have like two sides A, and say, well, A is not going to be here, A is going to be on that side. If I have C and B, and the angle in between, I can punch this in. It's very, those are the two times that I can use the cosine law to find things. So let's actually try this out. Just a quick example. Let's do 55, 32, and 26. And now I want to find, let's say I want to find this angle. Let's call it cos A, because that's what I'm going to be plugging in here. That'll be my A. So let's do, let's punch these in. So 55 squared. Let me write it here. 55 squared is equal to 26 squared plus 32 squared minus 2 times 26 times 32 times cos of A, which I don't know yet. So I can start bringing these over and subtracting them. So that'll give me 55 squared minus 26 squared minus 32 squared. And on this side, if I'm left with this term only, I want to get rid of all that and just isolate the cos A. That's all being multiplied by all this, so I can divide it. So now I'm left with this, and all I really have to do now is take the inverse cos of that, and I'll get the angle A. So if I punch all this into a calculator and get a number and do the inverse cos of that number, I should get an angle of about 143 degrees. And that is a example of us using the cosine law when we have three sides and we want an angle. But if we have, say, another example, say like this. B and C. 10.6 squared plus 22.9 squared minus 2 times 10.6 times 22.9 times cos of 26 degrees. Oh no. Let me write it back here. A squared equals 10.6 squared plus 22.9 squared minus 2 times 10.6 times 22.9 cos 26 degrees. Now all you have to do is solve for this. And if you just punch all that into a calculator, you get 200.42. And that's a squared, but a is going to be the square root of that, so you're going to get 14.16. And that's the example of us using this. If we have an angle and the sides on each of it. So yeah, that has been us using the cosine law. We can actually do one example where we use both the cosine and sine laws. So look at it like this. Say I have this triangle and I have angle A 60 degrees, but B, so that's capital B. I have this theta here, and I have C, which is also equal to 5.1, and this is equal to 8 meters. Now, say I wanted to solve for this angle. So right now, I cannot use the sine law because sine law requires me to have at least one angle and its opposite length to be able to do the other calculation. So I have this and that. So I could do sine theta over 5.1, but I don't have anything to compare to. I don't have 60 and B, I don't have A and 8. So I can solve for one of them. And let's try solving for B in this case. So I'm going to solve for B because remember my cosine law where I have the angle and the two sides. I can find out the opposite length. So I have this angle and measurements for the two sides. So let's punch that in. I got B squared is equal, because that's B. And I have the other two, A squared plus C squared minus 2 AC cos B. So if I was to plug this in, I would get B squared is equal to 5.1 squared plus 8 squared minus 2 times 5.1 times 8 times cos 16, sorry. And if I was to solve for this, I should get about 49.21, and B will be equal to the square root of 49.21, which is about 7 point something small. But I'll use 7 for now. So that's equal to 7. Now I have my sine 60 over 7. Now I can use the sine law and just solve for that. So my sine theta is equal to 5.1 sine 60 over 7. And is equal to the inverse sine 5.1 times sine 60 over 7. Punch this into a calculator and you will get theta is equal to 39 degrees. And there you have it. And you could even add this to 60. 180 minus 99 should give you 81 degrees. That's going to be this. Using the logic that the angles will add up to 180. So yeah, that has been the cosine law and everything, the sine law. Just a refresher. So I hope that was a good refresher, and we'll see you back here in the next video to do something more confusing. And that's all for this one. So, see you in the next one. Okay, so in this video we're going to be tackling 3D problems, three-dimensional problems involving trigonometry. So let's say we have a cliff. Say this is the cliff and this is the height up. Call it H, and I'll call this point A. And then I have this point here. I'm going to call it B. And I'll call this point C. And let's say that this is a right angle. It's going up. Elevation, this is the ground. This is the top of the cliff. And let's say I have another point here on the ground. Point D. And the angle here is going to be 42 degrees. And the angle, the length here is 68.5 meters. And I have an angle here of 63 degrees. And I have an elevation angle up here from the ground up of 38 degrees. This here is a right angle, but this one is not. This angle here is not a right angle. I'm just not good at drawing. So, let's start solving for H. Okay. So one of the first things I can do, I have two angles here very quickly. I can solve for this angle here. So 180 minus 42 minus 63 is equal to 75 degrees. And now I have that. So once I have that, I can actually look at, because I have this angle and its opposite length, I can use the sine law. Oh, let me do the other way around because I want this right here. I want that one right there. So, let's do 68.5 in the numerator and sine 75 in the denominator. And now I want this length here. I'll call that x. So I have x over sine 42, which is there. So now I'm able to use the sine law to solve for this line here, or that distance. So that'll give me x equals to sine 42 over sine 75 times 68.5. And if I put this into a calculator, I should get 47.45 meters. So that's 47.45. So now here I am again. I can use the sine law again. I have this is with this angle here, which I can calculate very easily because I know that that's a right angle triangle. So I know that actually, hold on, I don't need to use a sine law. If this is a right angle triangle, if I was to redraw this, that's 47.45, and that's an angle 38, and I want to find that, I can just use my 10 opposite over adjacent. So my h is going to be 47.45 times tan 38 degrees. Well, that worked out. So I'll just plug that into a calculator and get 37.1 meters. Well, that was a lot easier than it looked like it was going to be. Maybe we can do another one. Let me draw another problem for us. Let's try drawing a 3D shape. Let's see if I can do this. I'm gonna say that is one, and then I have another one over here, which is also a right angle, and then I have this right here. So this is going to get very confusing very quickly, but I'm gonna try my best not to confuse anybody. Let's try creating a grid here. Let's just say, let me use a different marker. What I'm about to draw is basically a Cartesian plane where this points north and then this will go like that. Let's pretend that's a straight line. So a couple things to note here is that from this line here, this red line, this angle is going to be 120 degrees. And then we have this line here, from here to go all the way around. That's going to be 230 degrees. And now I want to find the distance between A and B. Another thing that I'm given is this length here is 50. So, based on what we have, let's start going to work on this. So, the reason why we have these two measurements, very quickly I can redraw this and find this angle right here. Because if the whole thing is 230 and only up until there's 120, I can just subtract the two and get 110 degrees. So if I was to redraw that, that's 110, that's 50, this one right here. And now I can also look at what else can I take away from here. If I have 180, if this is a right angle and this is a right angle, let's see. What else can I take away from here? Okay, if I was, okay. If I was to look at here, 230 degrees to 120, then I could assume that if I was to look at it from a bird's eye view, if that's 230, then and the 3/4 way is 270, then I'm 40 degrees off here, 40 degrees off there. Okay, again, that doesn't do much for me. Oh, I understand what went wrong here. I forgot to give us some more information. So, if this was the Cartesian plane, and I was to look at it like that, the point at which this descends here, this is 38 degrees towards 8. 38 degrees. And then at this angle here, if I was to do a declining line, this one's going to be 35 degrees. I missed those two important points in this problem, because that would allow me to use my seat logic. 38 is the same as 38 degrees here. That gives me 38 degrees here and 35 here. So 38, 35. So now I'm in a much better place. So let's draw that bigger. Length here A, let's call that one B. Let's say this is 50, this angle is 38, this angle is 35. I'm looking for this. So yeah, let's start doing some problems. I remember 110 degrees. Let us start looking at how we can approach this problem. So, oh yeah, remember this is, these two are right angle triangles. So let's look at these ones individually. So we have on this side 50, a right angle triangle, and then an angle of 38. That is here. So if I wanted to find this B right here, I can just use tan 38 is equal to 50 over B, which is B is equal to tan 50 over tan 38. Similarly for this one, B is going to be equal to 64. So I can write that 64 approximately. And then same with this triangle here. That's 50. This one was 35. That's A. is equal to 50 over tan 35, which will give me A is equal to 71.4. So let's put that in here, 71.4. So, lo and behold, I have two lengths and an angle in between. And that means I can use my world famous cosine law. So let's start punching these numbers in. So I have x here. Let's do x squared is equal to 64 squared plus 71.4 squared minus 2 times 64 times 71.4 times cos of the opposite angle. And from here on out, it's just smooth sailing. It's all just calculator work. X is equal to about 111 meters. Wow, that was a lot of, it almost confused me, because I missed these points, these angles of depressions from the problem. I completely oversaw them, forgot about them, but yeah, very simple steps. Finding this angle in the middle here, the 110, was just because they gave me these two angles here, 120 to here, 230 to there, subtract those, and I get this angle in between. I have that, these angles of depression. If I use that Z logic of triangles, I have 38 there, 38 there. They told me these are right angle triangles. So, with the 38 and the 50, which they gave me for this,